Lab 2 video report, motioning of a falling object. So the objectives here are to apply Newton's second law to a real-world scenario, and we're doing this by determining the effects of gravity and drag on a falling object, this time a ping pong ball, and being able to predict those using a computer model. Concepts we have here are Newton's second law, which is force equals mass times acceleration. We have the position update formula and the velocity update formula on the left-hand side. The right-hand side, we have the gravitational force formula in vector form, which is negative mg, m being mass, g being the gravitational constant due to the Earth. And then we have the vector form of the drag force formula, which is equal to b times v ball squared, b being the drag constant, velocity of the ball being velocity of the ball. Then the net force is going to be equal to the gravitational force times the drag force. So on the right-hand side, you can see me dropping the ball from an initial height of 84 inches to the ground. And on the left-hand side, you can see my position versus time graph and my velocity versus time graph. And position versus time graph, you can see the ball is moving in the negative direction because the ball was dropped from the origin in the negative y direction. And the velocity versus time graph, you can see, is always decreasing, and it's constantly decreasing. And this is because there's an acceleration in the negative direction the entire time. Here we can see my predicted motion computer model for when the net force is equal to the gravitational force with no drag force. So on the left-hand side, we have the position versus time graph and the velocity versus time graph. And if you notice, the velocity versus time graph actually has a negative, constantly sloped line, and this indicates the negative 9.8 meters per second squared acceleration, which is constant the entire time because it's only the gravitational force acting on the ball. As you can see here, my initial position is 0, 0, 0 because I started from the origin. My initial velocity is 0, 0, 0 because I dropped the ball from rest. My g is 9.8 meters per second squared. This is the magnitude of the acceleration due to the gravity of the Earth. My j hat is the unit vector in the positive y-axis, so it's going 1 unit upwards. And then my w, which is equal to gravitational force, is equal to the negative mass of the ball times g times j hat. Then the net force is equal to the gravitational force. It's the only force acting on the ball. Then we have the velocity update formula, position update formula. Velocity update is final velocity equals initial velocity plus F net over mass of the ball times delta t, and position update formula is final position equals initial position plus the velocity of the ball delta t. So as you can see on the right-hand side, this is my predicted motion computer model for the ball, and this includes the drag force. Going back to the left-hand side, you see that the net force is equal to gravitational force plus the drag force, and the drag force is equal to the drag coefficient times the velocity of the ball squared. And you see on the velocity time graph on the bottom left that the velocity slowly starts to flatten out towards the end. Not enough because it doesn't reach terminal velocity, but the acceleration does begin to decrease a little bit, and that's because the drag force is actually acting against the gravitational force. Because those are going in opposite directions, the drag force actually works against the gravitational force to cancel those out. We have my drag coefficient, and that drag coefficient, I'd have to play around with it a little bit so I can make the computer model as close to the real life model as possible and making the final positions really almost identical. And then down here we have the drag force formula, and this is equal to the drag coefficient times the magnitude of velocity of the ball squared times j hat. So I had to make the magnitude of the velocity of the ball versus just the velocity because you cannot square a vector, but you can square a scalar and then multiply it times a vector. And then as you can see in the very bottom, the net force is equal to W plus FD, W being gravitational force and FD being the drag force. Right, you can see my position versus time graph for the simulation versus real life. When the simulation is without drag, see towards the end they start to separate a little bit. On the bottom right, you can see my simulation with drag, position versus time graph with the real life model, and at the end they have almost identical final positions. And then on the left-hand side, you can see all three of those models together, with real life being in blue, simulation without drag being in orange, and simulation with drag being in gray. And the simulation with drag is much closer final position than the simulation without drag compared to real life. Observations I made, the real life tracker does accurately show the effect of drag and gravity on the ping pong ball, while a simulation with drag makes the closest assumption to the motion of the ball, and then for time is less than 0.6 seconds. The force of gravity is greater than the drag force, so the ball continues to accelerate in a negative direction, and because of this continual acceleration and this non-zero net force, the ball does not reach terminal velocity. So what does this mean? Again, the net force does not equal 0 because the gravitational force is greater than the drag force through 0.6 seconds, and this means that the ball does not reach terminal velocity. What if we threw the ball downwards? This would give the ball an initial velocity in the negative y direction, and because of that initial velocity, there would be a greater drag force, again, due to the increased velocity, because drag force is dependent on the velocity of the ball. There would be an equal gravitational force because gravitational force is dependent on the mass of the ball and the gravitational constant due to the Earth. So the ball would reach its terminal velocity quicker because of that increased drag, and that increased drag with the consistent gravitational force, those two will cancel out quicker, making the F net 0, getting the ball to a constant velocity, which is known as the terminal velocity.